All right, welcome back. We are in section 2.1. We're going to start focusing on functions, function notation, what a function is, general types of functions, as well as domain and range we see here. But first, our first definition, a relation is any set of ordered pairs where the set of the first components is called the domain, and the set of second components is called the range. Now, another word for domain, generally in college algebra, our domain is our set of x values. If you're looking at your graph, you've got your x-axis and your y-axis, and you put together those x-y ordered pairs. So for example, if I have a point right here, it might be identified as 2, 4. This tells me that my x-coordinate is 2, my y-coordinate is 4. So my x-coordinate is my domain value, my y-coordinate is my range value. So domain is x, range is y, generally speaking. We classify the domain as the set of independent variables. It's what we plug in, so it's our input. The range is the set of dependent variables. What the range is the function value. It's the output that depends on what we plug in. So whatever my function is, I plug in an x, in this case I plug in 2, and I get out a y value. I get out 4. My range is also termed as our function value. If I ask you for a function value, I'm asking you for that y value at a certain x. All right, here's our first example. We're going to create a relation from the graph and then identify the domain and range. Now I want to reaffirm a relation is any set of ordered pairs. I don't have restrictions on what makes up a relation at all. A relation, even though there are no restrictions on it, will still have a domain and range. So I encourage you to go ahead and pause the video, read this explanation, and take a really good look at the graph. All right, so if you listened to me, you paused, you read, you interpreted this on your own, you can see that you've got the title of your graph, top 4 least corrupt and most corrupt countries. So we've got this corruption rating, and a high rating, it looks like, is a good thing. If it's got a high rating, that means they're less corrupt. If they've got a low rating, they're more corrupt. So there's two different sets I have. I've got my least corrupt countries, and I've got my most corrupt countries. And I can represent each of these as an ordered pair. For example, I can take the country Iceland and pair it with its corruption index. Finland has a 9.6. New Zealand also has a 9.6. Denmark, I don't know how they abbreviate Denmark. We're going to go DEN. Denmark has a 9.5. So those are our 4 least corrupt countries. It makes me wonder where we are. I'll have to look. Oh, right there. Sorry, there it is. I should have gone back and reread. And I don't have a year this is from, but we had a rating of 7.6. I wonder what it is now. Okay, then our most corrupt countries, we have Bangladesh at 1.7, tied with Chad at 1.7, and then at Haiti at 1.8, tied with Myanmar also at 1.8. So there are ordered pairs that represent our least and most corrupt countries. Now, we said that generally domain is the set of x values, range is the set of y values. This looks a little different, but our domain is still our input. We are looking up our country, that's our input, and our range, our output, is that score, that corruption index score. Okay, let's look at this next one down here. Take a second to read it. interpret the graph. Think of how you could represent these data points, this graph as data points, a set of ordered pairs. Well, it makes most sense to say our domain is going to be what is scored along our x value. So our domain is going to be age, and our range is going to be that survival percentage, that percent chance of survival. So if I do that, I see that if a 60-year-old has, if they want to survive to 70, that's an 86% chance. Want to survive to 80, there's a 60% chance that'll happen. Living to be 90, there's only a 24% chance that will happen. And you don't see many people who make it to 100 years of age, so there's a 2.7% chance of that happening. All right, so these are examples of how we come up with our input and our output. Generally speaking, our input is along our x-axis. Our output is what we place on our y-axis. Okay, function. A function is a relation. We've already defined a relation as any set of ordered pairs. It's a relation with some restrictions. A relation in which each element of the domain, remember that was our set of x values, corresponds to exactly one element of the range, which is our set of y values. So each x has exactly one y assigned to it. Another way of interpreting that is going to be that no two ordered pairs have the same first coordinate and different second coordinates because each x has exactly one y. Our relations are the relations we created on this other page. Are they both functions? Well, if I look up a country, each country has exactly one corruption index score. If I look up an age, each age has exactly one percentage assigned to it. So yes, those are both functions. If I'm looking at ordered pairs, that's how I figure out whether or not my ordered pair represents a function. If I'm looking at a graph, I use the vertical line test. Hopefully this is something that's just a review for you. The vertical line test says that if there's any vertical line that intersects a graph in more than one point, then the graph is not a function. It does not define y as a function of x. So we're going to use our vertical line test to identify graphs in which y is a function of x. Remember, y is my function value. I plug in an x, I get out a y. That's my function value. If I plug in an x and I get out more than one option for y, it's not a function. So for example, if I plug in 1 here for x, I get out two different function values, a positive function value and a negative function value. That fails the vertical line test, so it is not a function. But for b, if I plug in an x, I only get out one y value, passes the vertical line test. There's nowhere I can draw a vertical line and it's going to cross more than one place, so yes, it is a function. C passes my vertical line test. There's no vertical line that crosses more than one place, so yes, it's a function. What about D? Well, this vertical line, my y-axis, is fine. But if I draw another vertical line over here, it crosses in more than one place, so it is not a function. That yes means that they are a function. No is not a function. And then we've got these really interesting squiggly things going on down here. So check each of those to see whether it is a function or is not a function. Pause the video, go over that. You should get these results according to the vertical line test. Then it also says let's discuss domain and range. So let's do that. Let's stop and discuss domain and range. The domain and range, both of this function, are restricted. I can see that this function exists along a domain from some negative value to a positive value. So we've got upper and lower limits on our domain. And then we also have upper and lower limits on our range. So our domain, let's say it goes from I'm just going to throw in some numbers here. It goes from -5 to 4. That's the domain of that function. And let's say this range goes from -3 to +3. Range goes from -3 to +3. There are upper and lower limits on the domain and range for this relation. This relation is not a function. On B, however, I see that there are arrows on both ends, so it keeps going forever in both directions, which means that this line extends forever and there are no limits. It's going both up and down, it's going both left and right, so my domain and range is all real numbers from -infinity to +infinity. No limits. Do you see another function that has no limits on domain and range, or a range, not a range, a relation that has no limits? Well, this one also, this is a relation, not a function, but the domain and range here are going to be all real numbers, no limits on that domain and range. Arrows going on, up and down, left and right, forever. We got interesting, fun stuff happening here, but it's going to just keep going. Probably this one, actually, because, well, no, I take that back because it looks like this flattens out. So probably we've got a limit there. Definitely got limits on both domain and range here, upper and lower limits for domain and range. We've got a lower limit for our range here. We've got a minimum value, but it goes up forever. We've got a limit on our domain here because it starts at this x value 0 and then it goes forever to the right. Alright, so we've kind of talked about domain and range there. Let's look at these two relations and talk about whether or not these are functions, and then give domain and range for each of these. Now, when I have continuous graphs, my domain and range are going to be represented by intervals. Let's go ahead and do domain and range here. My domain, the x value it starts at is 0, and it goes on forever to +infinity. My range, because these arrows are going on and on, it keeps going up and out, up and out, up and down and out. My range is going to be all real numbers. So I'm writing those as intervals. Circle here, let's say our circle, well, our circle has upper and lower limits, so it's going to, domain and range is going to look more like this. When I have a set of ordered pairs listed, these two relations, I've got sets of ordered pairs. Let's make this A and this B. Relation A, my domain is going to be, I've got to list it in fancy braces because I've got individual values. 3, 4 are the only values in my domain. When I look at the range, I've got 4, 5, 4, 5, so I've got 4 and 5 in my range. Is this a function? Well, remember my definition for function is that each x corresponds to exactly one y. And I could set this up and say, okay, my domain includes 3 and 4. My range includes 4 and 5. And how are they connected? Well, 3 pairs with 4, 3 also pairs with 5. Anytime that happens, I know immediately that this is not a function. So there is a visualization in addition to what you have going on in your ordered pairs. So look at B, try B, list domain and range, and determine whether or not B is a function. Now I see something interesting going on with B. I only have one value in my range, but my definition for function says that each x is assigned exactly one y. It doesn't say anything about whether or not that y repeats. And I see that if I wanted to set up my circles again for domain and range, my domain has 3 values, my range just has 1 value, but each of those x values pairs to only one y value, so that is a function. That's a function. It works. Now, we're defining y as a function of x. Are there any relations that contain y squared that do not define y as a function of x, and why? So let's take a look at that. What if we have a y squared? Basically is what we're asking. What happens if we have a y squared? Well, if I want to solve for y, I'm going to move this x squared over. So now I have y squared equals a negative x squared plus 3, or 3 minus x squared. And let's think about how we would solve this. If I'm solving for y, squared term equals to something, we're going to use our square root property. Well, when we use our square root property, we take the square root of both sides. We have to remember that plus or minus. And when we set up to say, okay, I've got to remember that plus or minus, then that means that I've got two solutions. I've got whatever this comes out to be, I've got the positive value of that, and I've got the negative value of that. So I've got two solutions. Anytime I start with a y square, y is not defined as a function of x because it gives me two solutions. There's not just one output for each input. Okay, remember to pause, go back over, sit and think about some things if you are getting overwhelmed and need that break. You've got control of the lecture here. Function notation. Y is defined as the value of the function at x. That's our definition of a function. Our notation, instead of writing a y, we write f of x. That means the function value at x. So that y equals 2x plus 3 becomes f of x equals 2x plus 3. That's my difference in notation. That's my function notation, and then we can evaluate the function by plugging in something for that x. So my function notation says, okay, I want the function value, I want the y value where x is 5. Well, this is my function. Where x is 5, that means I take out that x and I replace it with a 5. And I evaluate the function where x is 5, and I get a function value of 13, which means for x is 5, y value is 13. I plug in an input, I get out an output. I get out a function value. And then let's do that again. What if x is negative 1? Well, for this function, if x is negative 1, I get out a function value of 1. So for this function where x is negative 1, my y value is 1. And then we get a little bit more interesting down here. I'm replacing x with x plus 2. So now I have 2 times x plus 2 plus 3. Whatever I'm giving you for x, that's what I'm plugging in where x was in my function. Now I got to do this order of operations correctly, distribute across the addition. So I have 2x plus 4 plus 3, which is 2x plus 7. That doesn't lend itself to a nice, pretty little ordered pair, but it does give us the function value if I were to use x plus 2. All right, let's do a little more with domain and range, x and y intercepts, and finding some missing function values. For this first one, this shape is a parabola, which we're going to talk about parent functions here shortly. This means that I've got a quadratic function. Y equals f of x is my function. First, I need to answer these two questions down here. F of x, so that's an x value. Well, where x is negative 2, I'm going to go travel and find my, I'm going to find my function. My function is here. So where x is negative 2, y is negative 3. And where x is positive 2, so where x is negative 2, y is negative 3. And where x is positive 2, right here, I've got to find my function. And it looks like it would be up here at 5 to me. I think we would make it all the way to 5. So positive 2, positive 5. Those are the 2 points that I'm being asked about, where x is negative 2, y is negative 3. Where if x is positive 2, I'm up here at 5. Okay, the next thing that I want to do is find domain and range. So let's figure out what's going on for this function. I see that it has arrows on both ends, so it's traveling up and out forever, which means it's just going to get wider and wider and wider and wider. That means that my domain does not have any restrictions. My domain is going to be all real numbers, from negative infinity to positive infinity, all real numbers. My range is my set of y values, though. I start at the bottom and I work my way up, and my range does not start until right here. This is the first place I see my function graph start. That's at negative 4. I have a lower limit. This is a minimum value. So my range starts at negative 4 and it goes up forever. Notice that if I'm doing infinities, it's always curved parentheses because I never get there. If I'm doing a value that is included and it's a limit, then I use square brackets for my interval. So I've done domain and range. I did the missing function values. Let's do our x and y intercepts. I cross the x-axis here and here. I cross the y-axis there. I will only ever have one y-intercept if it's a function because it has to pass the vertical line test. My y-intercept, where x is 0, I have a y-intercept, and this y-intercept is negative 3. I can have more than one x-intercept. In this case, I have 2. X-intercepts happen where y is 0. So I've got negative 3, 0, and I've also got positive 1, 0 as the locations for my x-intercepts. All right, so that's the information we were asked to do for each of these graphs. For this one, I can see that my function values that I'm asked for, if f of x, so x is negative 1, my function value is 2. Where x is 3, my function value is 4. So those are my missing values. Domain, again, I've got arrows on the ends. It goes up and out forever, so my domain is going to be all real numbers. Never get there, so my infinities are curved parentheses at the end. My range, again, has a minimum value. If I'm traveling up from negative infinity up my y-axis, my function first starts here at the y value 1. So my range has a minimum of positive 1, and then it goes on forever to positive infinity. The next thing I need to do are my intercepts. Well, this function does not cross the x-axis, so I have no x-intercepts. There are none. I could also have written that as NA, not applicable. My y-intercept, though, is right there, where x is 0, y is 1. Again, if it's a function, I'll only ever have one y-intercept because it has to pass that vertical line test. Alright, so let's look at these 3 graphs on the next page. Now, something I noticed right away about these 3 graphs is that my ends are not both arrows. This one has one arrow. It has one ending point and it has one arrow. Some of these ending points are filled in and included. This ending point is an open circle, which means that point is not included. This graph is going to go up almost to this point, but not quite. So it doesn't reach where x is 5. It reaches where x is 4.999999999, but not where x is 5. First things first, though, my function value, where x is 3, y would be 1. So that would be an ordered pair on my graph, 3, 1. The next thing that we tackle is domain, and I see that I have limits. If I read my domain like I read a book from left to right, my function starts when x is 0, and it keeps going almost but not including where x would be 5. So my domain is from 0 to 5 on the x-axis. I get to include where x is 0 because that's filled in. I don't include where x is 5 because it's not filled in. So we read our x-axis from left to right like we read a book. To find our range, we read our y-axis from bottom to top. We always go least to greatest. So we read up our y-axis. As I go up from negative infinity, I see that my first y value is here at -1, so that's my lower limit. As I keep reading, I see that my upper limit is going to be just before I get to y is 5, so that is an open circle there. So my range goes on the y-axis from -1 to 5. -1 is filled in, so it's included. 5 is an open circle, so it is not included. And then x and y intercepts. I have one y-intercept and one x-intercept. My x-intercepts happen where y is 0. My y-intercepts happen where x is 0. All right, I am not going to talk you through 4 and 5. I want you to pause the video, do your best to answer 4 and 5, and then restart the video and see what my answers are. I'm going to put my answers up, but I'm not going to talk you through them. Okay. All right. Ordered pairs for your x and y intercepts. Notice that. All right. Let's talk about even and odd functions and symmetry. Now, this next page is going to be kind of, we're going to be working on parent functions, talking about even and odd functions and symmetry. I want you to, if you're been a lot, I want you to take a break. I want you to take a breath, walk around, get something to drink, because I want your head fresh for this. Now, if a function is even, then we say it is symmetric about the y-axis. That means I can fold my graph and the sides are going to match up if I fold it on the y-axis. Do you remember when you were little, maybe you'd put paint on one side of the paper and you'd fold the paper in half and you'd make a butterfly or a heart or whatever was going on, the two sides would match. So it is even and if it's symmetric about the y-axis. That means that whatever I have going on over here is going to reflect and go on over here, and the two sides are going to match. This is my axis of symmetry, the y-axis. I did my best to show that these two sides match. That's an even function. Now, this happens mathematically if I plug in a negative value for x and nothing changes. I get out exactly what I started with. Okay? Odd function happens when it is symmetric about the origin. Now, the origin is that place where your axes meet. In the middle right there, that's my origin. Something that is symmetric about the origin has a twist in the middle. So, and I have a hard time with doing something creative with this, so I'm just going to be really basic. So if this is what's going on in the upper left, and I've got an odd function that has origin symmetry, then this is what's going on my lower right. I've got this twist in the middle, okay? And to get symmetric about the origin. That's my origin. Symmetry. If I've got an odd function. And to get an odd function mathematically, I plug in that negative x and it gives me the opposite of what I started with. Now, this is not the only symmetry test that exists, but this is the symmetry test that we are going to use. It either nothing, I plug in a negative x, nothing happens, nothing changes, and I've got even symmetry. I plug in a negative x, everything changes sign, so I have the opposite of what I started with, and I have odd function symmetry around the origin. The only other option that I have is that some things change, not everything changes. So I don't say there is no symmetry, I say there is no predictable symmetry. There may be a type of symmetry that this test doesn't give me, but we can't predict it with this test. Just know that it's not symmetric about the y-axis or the origin. And what that shows up when I plug in a negative x and some terms change sign. Not everything changes sign, but some terms change sign. So something starts positive, ends up negative. Something starts negative and ends up positive, but not every term. Okay, that's information, good information. We're going to talk about even, odd, and neither as symmetric options for symmetry. Get it down, keep it in your notes, keep it handy. Now, the last thing we're going to do together in this section is our parent functions in symmetry. These are our parent functions from our families of functions, and let's do this explanation here together. Each type of function has a specific shape for its graph. Hopefully you already know, for example, if you have a quadratic function, x squared, that is always going to give you a graph that is a parabola every single time. That shape is maintained for that function type no matter what you do to the equation. Just like I said, quadratic equation, always going to be a parabola. The most basic function for each type is called the parent function for that family of functions. Makes sense, right? You have a family of functions. The parent is the most basic one. It's what you start with. Now, the parent function goes through transformations in the form of shifts. So it can go up or down. Shifts can go, up or down, left or right. So my shifts can go horizontal shifts, left or right, or vertical shifts, up and down. Flips or reflections on either axis and stretches or shrinks. Okay, still going to be the expected shape. So I can turn it around, flip it over, stretch it out, squish it together, but it's still the same basic shape. All right, we're going to focus primarily for right now on these first 6, but I'm going to go ahead and give you all 9 of these parent functions because it's good to go ahead and start looking at the basic shapes. Right here, f of x equals x. Remember, f of x is the same thing as y. That's my linear function. This is the parent linear function right here. Parent linear function. This next one, f of x equals, how do we read that symbol? Absolute value. That's my parent absolute value function. Absolute value function is always, always, always a V shape. The parent absolute value function has a minimum function value of 0. Then we've got our quadratic function, our x squared. Quadratic function's always going to be that U, that parabola shape. parent quadratic function opens up just so and has a minimum value for the range of 0. Down here we've got, that's an x cubed. F of x equals x cubed, so that's my cubic function. All of these are functions, they all pass the the vertical line test. X cubed, y equals x cubed, f of x is x cubed. Domain and range, both are all real numbers, goes up and down forever. Over here, we've got, what is this symbol? It's my square root. Square root function has a limit on the domain and the range. The parent has that limit at 0, the origin, 0, 0. And then, hopefully you notice the similarity in the shapes of these two functions. These are what we call inverses. We have a cubic function, and this one, that index is 3. That is my cube root function. I took it and I flipped it across the line, y equals x. So I have the cube root function. Now, before we talk about these last 3, I want to apply what we learned about even and odd symmetry. Can't get it to fit. An even function is symmetric about the y-axis. I can fold it on the y-axis, fold it like a hot dog, and the sides match up. So out of these 6 functions, do you see anything that's going to be an even function? If I fold my paper on the y-axis, the 2 sides would match up. Well, looky there, right there. These 2 are both even functions. So let's mark that. These 2 are both even functions. I have y-axis symmetry. I can fold my graph on the y-axis and the 2 sides are going to match. Now, this is true for the parent, but if I shift that parabola over left or right, shift that v over left or right, it may not be true for all of them. For the parent function. Because mathematically, f of x equals x squared, if I plug in a negative x and I square that, I get out the same thing I started with, positive x squared. Nothing changes. Over here, if I plug in a negative x, mathematically, the absolute value of negative x is just x. Exactly what I started with. Nothing changed. These are even function examples. They are symmetric on the y-axis. Then my other symmetry type that we went over was odd symmetry, the symmetric about the origin. When I plug in a negative and everything changes. I got that twist in the middle. Up left, lower right. Do we see anything with a twist in the middle? Up left, lower right, up right, lower left. Well, this parent linear function does that. Down here, my cubic function does that. And even my cube root function does that. So these 3 functions all come out to be odd functions. For the parent, these are odd functions. Just the parent, not the whole family. They have origin symmetry. If I take f of x equals x and I plug in a negative x, I get out the opposite of what I started with. So it's going to be an odd function. If I take f of x equals f of negative x. Got in a hurry. F of negative x equals a negative x cubed. A negative times a negative times a negative is still negative. I get out a negative x cubed, which is the opposite of what I started with. Opposite of what I started with. Over here, if I do f of negative x and I take the cube root of that negative x, well, these 2 things undo each other, so the cube root of a negative x is a negative x. Oh, it's the negative cube root of x. Sorry, that's negative cube root of x is how that's going to come out. It's going to simplify to be, which is the opposite of what I started with. Sorry, I got hung up there. This square root function, it is neither. Neither even nor odd, so I have no predictable symmetry. This is odd. Okay. Last three functions. I promised you we're not going to be working with those right away, but we are eventually going to get to them, so we're going to go ahead and introduce them. These three functions show up in units 3 and 4. This 1 over x, f of x is 1 over x, is my rational function. You can see that you've got places where my function is undefined. We call these vertical and horizontal asymptotes. Lines the function gets closer to but does not cross. This has a horizontal asymptote. This one has a vertical asymptote. F of x equals e to the x is an exponential function because my variable x is in the exponent. F of x equals ln of x is a logarithmic function because that is a log base e. That ln represents log base e. So again, we aren't going to get to these three until units 3 and 4. So don't stress about that, but if you see them again in something, they pass our vertical line test. They are functions, but they're special types of functions.